Hello girls, this is the recording for lecture 1. But before I go into the lecture, I want to first go over the syllabus for this course, mainly the timetable. As we can see, this course consists mainly of architectural acoustics and lighting and daylighting. So we're going to have first 4 lectures in architectural acoustics. Then we're going to have a major exam in architectural acoustics to cover all the topics in acoustics. Then we're going to go to learn more about lighting, daylighting, then electric lighting, and have a major exam about lighting and daylighting. So this is the course outline. So lecture 1 is one of the 4 lectures for architecture acoustics. Now for each class you're going to have a quiz, a weekly quiz. For lecture 1 I'm going to give you the quiz on the next class, so it's not going to be online at home. The grades for this assessment is going to be 20% for each major exam, then 20% for the total of the assignments and the project and quizzes. Now, as it goes for the Moodle quiz, for each lecture we're going to have a quiz. So we're going to have a total of 10 quizzes. So I'm going to take the average of 8 of them and omit the lowest 2 of them. So in case you couldn't do a quiz, you missed it because of some excuse you have, that is fine. I'm not going to take into consideration the 0 mark. Okay. Now let's start with the lecture. So this is the first lecture, as I said earlier. This is in architecture acoustics. Now, as we can see in these images, these are like examples of how architecture acoustics is being used in the design and affecting the interior of spaces. So these are the content for this lecture, lecture 1. We're going to first have a look about the introduction. We're going to first introduce the architecture acoustics to you. Then we're going to have an overview over the history of architecture acoustics. Then we're going to talk about the physics of sound, the biology of sound, and perception of sound. Then at the end, we're going to talk about sound and health. So first, let's have an introduction about acoustics. So how important is acoustical design in architecture? Actually, it's very important, but usually it's being neglected because usually if you neglect acoustics in architecture, you're not going to have any hazard issues or any fatal issues. But at the end, you're going to affect drastically the quality of your design and your project, especially if it requires like it has some acoustical needs. Now, as an architect, we don't need to know much about acoustics to implement it in our design. We need to know the basics and principles of acoustics so we can use it in our design and have a quality design. Now let's have a look at a couple of examples where acoustics were actually important but somehow neglected and need to be fixed. Now in this example, this is the Lincoln Center in New York. As we can see, there's a before and after. The thing is, when they designed it back then, it was years ago, the design was looking good, but when they actually started using the space, they had a lot of acoustical problems and issues. They tried to fix it by retrofitting it, adding a couple of acoustic panels, but the issue wasn't solved properly. So eventually, they had to renovate the whole place all over again from zero, which has cost them a lot of money. Now the thing is, this is an example of how costly it can be if you didn't design well from the start. So you need to be careful in these spaces, and you need to consider acoustics from the start. Now this is another example where acoustics is important. They were able to fix the issue on the spot. In this example, we can see a classroom. In this classroom, probably the problem was there's echo at the back of the classroom. So this is caused usually by the echo reflected of the surfaces, the reflective surfaces at the back. The window, as we can see in here, this is reflective. So they wanted to stop the echo, and which causes the disturbance for the heaters in the space. So they had to put these acoustic panels which were able to absorb the sound and avoid it from reflecting into the ears of people sitting here, thus avoid the echoes. This is another example. Now, this example is like telling you there's an issue in here, but the thing is, the issue is not being addressed because it's not major, it's not being noticed much, but it's causing the space to be of low quality. As we can see in this image, as we can see here, people are sitting. We can see people like trying to hear each other. I can figure out from this image that a person sitting here, a person talking here, that this person would hear this one more than he would hear someone in front of him. So at least there should be a partition in between. Another thing we have to look at in this picture is, for example, the high ceiling. Now, high ceiling, this allows for more reflection. That's causing more echoes. Furthermore, as we can see, the windows and the ceiling, they are made of reflective materials, which definitely will reflect back the sounds to the people in here, which is going to cause a lot of noise. Now, overall, the main goals of architectural acoustics are two things. So, in every situation, there's something speaking, okay, or not speaking, like producing a kind of information through sound, and there are other sounds trying to obscure that sound. So, we want to omit these sounds. So, the two main goals are to maximize the hearing of speech or music, whatever they want to hear. Okay, so maximize the source of sound you want to hear and decrease the source of noise that is obstructing the hearing process of the main sound. So acoustics are like lighting, both acoustics and lighting. We always like aim for quality, not quantity. Meaning, it's not like in acoustics, it's not a perfect design to increase the loudness of a sound. The perfect design would be to focus on the main sound and try as much as possible to avoid the other noises in the space. So this is where quality is much more important than quantity. The same thing applies for lighting, which we are going to have a look at in other lectures in this course. Now, the second thing we're going to go over in this lecture is the history of architectural acoustics. Now, years ago, there wasn't something called architectural acoustics. It was like built, it's within the architecture itself. So the architects, they had some acoustic techniques, but they didn't like separate it from architecture. Now that was they started in ancient Greeks and Roman theaters, as we can see in this example. Later on, they were like me. They had a couple of studies, as we can see in here. 18th century, they started like learning about the science of general acoustics. Later on, they were more advanced in that field by German Herman. And later on, the 20th century, they started like studying the science of architectural acoustics separately. Now let's get back to history of architectural acoustics in ancient Greeks and Romans, in the theaters more specifically. Now when we have a look at this image in here, we see there's like a couple of strategies being used to enhance the sound in here to reach the audience. The the first strategy they have used is the semicircular seating. The semicircular seating, it's helping all the audience to be as close as possible to the source. So this is my source in here in the middle. So the person sitting here will hear the same as the person sitting here. Now the second strategy they have used is the raised stage. Raised stage would allow more people to hear. So people in here will hear, people at the back will hear more. So if it was a lower, the stage was low, only people in the front would hear. Now when I raised the stage, this allowed for more people at all levels to hear. Okay. Now the second thing is we need to look at in here. Now, as we said earlier, we have two main goals in architectural acoustics. One is to enhance the sound source, and the other one is to obscure the noise. So first thing in here, how did they enhance or increase the sound source? So if the source was in here in the center or in the stage in here. So first thing, they raised the stage. The second thing, as you can see in here, the stage has a back wall and an upper, like a small ceiling and side walls. This would allow the sound of the source in here to reflect to reflect back into the audience. Meaning, if we have a look in here, this is the sound source in here. So the sound is traveling in all directions. The sound that is traveling in the back direction will be reflected back to the audience. So this would allow the sound to increase in loudness. Another thing is the addition, like I said earlier, the addition of the side walls, like as we can see in here in some stages. This is called the proscenium arch. Also, this one has the same function as is described now, of reflecting the sound to the audience more. Another thing, let's talk about the materials of the surfaces. Definitely, if I want to reflect back the sound into the audience using these walls and ceiling in here, these surfaces have to be of reflective material. Another thing we have to look at is the stepped seating. The idea of the stepped seating is to allow all audience at all levels to see and actually hear the performer. Now, let's imagine that the seats were like flat. If it was flat, the person sitting at the back will have the sound being obstructed by people sitting in the front. Now, there's a rule in sound, which is whatever you can see, you can hear. So the same thing goes the same as light. Nothing obstructs the light. Nothing is gonna obstruct also the sound rays. If you can see well, you can hear well. Now let's have a look at other things or strategies they have used back then, and they were related to acoustics in architecture. Now we have something called echo and reverberation. Now before I continue, let's first discuss these two terms. Echo is like hearing the distinctive sound again at some point in here. For example, you're sitting somewhere, then for example, you speak one word, then you'll hear that word not only once, you'll hear it like you speak it, then you're going to hear it again, coming maybe after 1 second, 2 seconds to you. So this is echo. You are hearing a distinctive word again. Now reverberation is that sound is going to travel at a shorter time. For example, that word is going to overlap the first word. So you're not going to hear that word again, but you're going to hear like words like overlapping each other. So this is called reverberation. Reverberation, you're going to hear like augmentation of the sound, but you're not going to hear distinctively the words being reflected. Definitely these terms will be discussed later on in more details, but for this example, because I want to discuss reverberation echo in these examples here. So back then, they were using echoes and reverberation according to the need, meaning sometimes I need echo and reverberation, sometimes I don't need echo and reverberation. And for example, in churches back then, they had two different choices. One of them was like to give a speech. Giving a speech is only one person being talking, and this person doesn't want to hear an echo of his voice. Also, the people listening to him don't want to hear any echo of his speech. So in this situation, we want to have a zero echo and the least possible reverberation possible in that space. So we want that space to be absorptive of the sound to avoid any reflection of the sound. Now, let's have a look at the other scenario where I want to actually increase the reverberation. Now, these scenarios happen when, for example, you have a musical event happening in a space. If you have any musical event, so you want to hear that sound, like overlapping of sound will actually make the music more appealing to the listener. So there's no action, there's no words being listened to, so that's fine to overlap the sounds over each other, like the sounds of the instruments or the music. So in this case, when I have a musical event, then I need a space that is reflective, that is large, that would allow the reverberation to be longer. Okay? So this is what they've done. In churches, they had areas where enhance the reverberation, more reflective materials, large spaces, reflective surfaces. This would allow to the musical events and chanting to be good. Now let's talk about the sound transmission through walls and doors. Back then we have walls and doors. Definitely the walls, the thicker the wall, the better. So the thicker the wall, the more decrease in sound transmission you have between one space and the other. So the higher the privacy you have. Now let's have a look at the doors. Now the doors, they are not made of stones, they are made of wood. The thing is, in back then, they wanted to increase the privacy between adjacent spaces that are connected by a door. So, for example, they used solid wood doors, and if they wanted to increase more the privacy, they had like more than one layer. Now, why did they have more than one layer instead of having one thick layer inside that door? In acoustics, if you have, for example, 10 centimeter of wood attached to 10 centimeter of wood, that would insulate more and like decrease the sound transmission more than having a 20 centimeter thickness of solid wood. So they were using that strategy and technique back then since ancient Greeks and Romans. As we can see in here, multiple layers are better than one layer of equal mass and thickness. Now, another use of acoustics back then as well, we had these two examples, detecting underground digging and detecting house intruders. Both of them, they were like used for important issues as detecting danger or intruders to their palace or their buildings. So the first one is using the principles of structure-borne sound. Now, before I talk about this example, I want to first explain what does structure-borne sound mean and what does airborne sound mean. Airborne sound is the sound that is being transmitted from one area to the other through the medium of air. For example, you are inside a space, one person is standing in one corner and the other person is standing in the opposite corner. So when they speak to each other, the sound is being transmitted through air between them. Now, if you, for example, put your ear on a wall and try to listen to the sound or the speech of someone on the other side of the room, on the other room. So now sound is being transferred through the medium of the wall, through the structure. So now this transmission is called structure-borne sound. Now, examples of structure-borne sound usually are if you are digging on a wall or you are stepping on a floor and people on the lower floor are hearing the steps of people at the upper floor. So these are examples of structure-borne sound. Now, structure-borne sound usually travels quicker and louder than the airborne sound. So they used this characteristic of structure-borne sound to actually detect underground digging. So they couldn't hear it much in the airborne, like at the top of the house, but they were able to actually detect it more in the basement of the house, where they could attach certain elements, such as these brass vessels, to the walls, where they could vibrate when something happens to the structure. Now the structure is like attached to the earth, so if there's any nearby digging happening in the earth, this digging is going to transfer to the walls of the basement at a high speed, and that's being detected by these vessels when they move and create a noise. Now let's have a look at the second example, which is detecting house intruders. This was, for example, a palace in Japan. Now, as we can see in Japan, their houses were made of paper-like materials. The walls were thin, the floor were like creating a squeaky sound when you step on. So they used these characteristics to detect any intruder entering the space. Okay, now let's talk about the physics of sound. Now, sound is a form of energy, and you've probably took this before in physics. That we have different types of waves. The sound wave is a longitudinal type wave, as we can see in here. So it's a series of compressions and decompressions. So the areas of compressions are, as we can see in here, these are creating the sound you have. Now, the higher the compression, the higher the amplitude. So you might have like two sounds of the same, let's say, wavelength in here, but like they have the same information. But the thing is, one of them is louder or higher volume. So the higher volume is the intensity in here. The higher the intensity, this means higher volume. And if you have like the distance between one compression and the other, like it converts into the what you hear. So we have something called wavelength and we have something called frequency. Now let's first talk about the wavelength. So the wavelength is the distance between one compression and the other. So this is a compression in here, this is a compression. Now the amplitude is the distance between the top of the compression to the lower part of the decompression. And as we said earlier, amplitude is related to volume and loudness. Wavelength is related to its frequency, to what type of sound you are hearing. Okay, so this is the wavelength. As we can see, wavelength is being measured in either meters or feet, and different wavelengths create different tones or different pitch. Now you can characterize a sound by its wavelength, or you can characterize it by its frequency. Now we will talk about frequency in the next slide. Now first I'll talk about the peak of the wave. Peak of the wave, like I told you, is the top of the compression. Trough of the wave is the lower part, and the amplitude is the loudness or the volume. Now there's a difference between amplitude, volume, and loudness. Now amplitude and volume, they are almost the same. Like they are the objective number of the sound amplitude, like sound. I'm not gonna say loudness, sound volume. Now, our ears are sensitive to certain frequencies more than the other. So what I'm going to hear might be, for example, we have two different sounds, two different frequency of the same volume, but one of them I will hear it as loudness more than the other. This is because my ear will be sensitive to one more than the other. This is why I can't say loudness is the exact thing as amplitude or volume. Loudness depends on the perception of our human ear. Now let's talk about the frequency. Now the frequency is, we wanted to have another measurement for the sound, or another measurement, not measurement for the sound, another way to actually differentiate one sound to the other, another characteristic. So as I said earlier, how do you differentiate between one sound and the other? It's by the difference in their wavelength. So different wavelength, different sounds. So they wanted to have another way to differentiate between different sounds, which is the frequency of how many waves happen in 1 minute, for example, or in a certain distance. For example, as we can see in here, these two different sounds, they are like traveling 1 second. So in 1 second, the sound travels around 344 meters. As we can see, type A, sound A, has actually a very short wavelength. So it travels more waves in 1 second. Now, while this one has a long wavelength, so it travels less waves in 1 second. So according to this, as we can see in here, so if you have more waves in 1 second, it's the more the waves in 1 second, the more you're going to feel the sound is being like pitchy. Okay, so the higher the frequency. So the number of how many waves you have in 1 second is actually the frequency. So in 1 second, we have like a constant distance being traveled by sound, which is 344. So because this number is constant, so we can, like, if you know the wavelength, you can definitely know the frequency from the wavelength because the speed is actually constant. So you need to learn this number in here, the speed of sound. The speed of sound is, as I said earlier, is 344 meters per second. And this is the equation. So speed is wavelength times frequency. So how many times the wave travels in this 1 second, and what is the wavelength for each wave. Now, so let's have a look at difference between two wavelengths and two frequencies. So a sound with higher frequency will have a sound will be a sound with higher pitch. A sound of smaller wavelength will be a sound of higher pitch. Okay. So sounds are usually described by their frequency. They're not usually described by their wavelength. In acoustics and in architecture, you don't use for example, you don't name a sound. For example, say a sound. This sound is 0.4 meters wavelength. No, you say, for example, 4,000 hertz, 10,000 hertz. This is how you differentiate between different sounds. So this is the unit being used, or the term being used usually. Now, as I said earlier, the human ear is not equally sensitive to all frequencies of sound. So this, we have to take note of this one as well. So let's have a look at the sound sources. How this information would help me as a person. So this actually helps us, as we all know, in our speech we have something called vowels and we have consonants. So usually the vowels we hear them at a lower loudness, and the consonants you hear them at a higher loudness. This is how you get the information from a word. So like the vowels are like the transition between one letter to the other, and they are of a like lowest loudness. So apparently the frequency of the vowels are like we are less sensitive to, and the frequencies of the consonants we are more sensitive to because we hear them more. So as we can see in here, also we want to know our speech. What is the wavelength in our speech, or what is the sound in our speech? Actually, our speech is a mixture of different frequencies combined together. Each letter is a frequency by itself. Each like sound you are creating, we are creating different sounds combined together, like being traveled after each other. This is how you are like creating the speech or the information of through talking. Now, if you like vibrate a tuning fork, this is what you are creating, a very pure sound of a definite frequency. Now, this is, as we can see here, this is the frequency or the output of a speaker. This is similar to a person speaking, by the way. So, in here, let's have a look at the tuning fork.
We can record pressure variations in sound waves with this kind of instrument.
So as we can see in here, this is the sound. The sound is actually a compression and decompression of the air particles. So, and this machine is just like translating the compressions into a graph.
Condensations cause the
So when we have a compression, we're having a peak. When we're having a decompression, it's the trough at
So far, we've seen how
the
sound
bottom.
waves are produced. Sounds, loudness, pitch, and loudness.
Now let's see in here, we have this tuning fork. So when they hit it,
Every sound sets
it's
up a
like
disturbance in the transmitting
the
medium.
vibration is being constant. Like the vibrating inside, vibrating outside is being constant.
The larger the disturbance or displacement of the individual particles, the greater is the height of its graph above
So
the
as we
neutral
can
line.
see, it's more intense, so it's creating a higher volume, but it's the same
And it is amplitude
sound,
that
it's the same
determines
frequency.
loudness. As its loudness increases. Next, let us consider pitch, the auditory effect of frequency.
Now here he is talking about different sounds, different frequencies, which is also called pitch. So we're going to listen to them and hear the difference.
Next, we hear G below middle C. And now the sound of C below middle C.
So see, you can hear the first one being of a higher pitch. Now higher pitch means like there's more waves traveling quickly within 1 second, as we can see in this one. Now the second one, okay, this one has a higher pitch. See, because it has a higher pitch, you see too many waves happening at the same time.
Therefore, its frequency is greater.
You can have a look at the video yourselves. It's linked in the lecture. Now let's talk about how the sound waves interact in with a solid material. Now there are different types of interactions. Now we've spoke earlier about the echo. If echo is the interaction of reflection in a space. So these interactions usually have they are dependent on many other factors, which could be the size, surface feature of the materials and space, and composition of the material. Also, it depends on the wavelength itself. What do I mean by wavelength or frequency itself? The thing is, the wavelength size of sounds ranges from the lowest of 4 centimeter to 10 meter. Imagine you have a space that is, let's say, of a size 4 meter by 4 meter. The wave of 10 meters, this wave of 10 meters is not going to travel the whole wave within this space. So you actually can't predict how it's going to reflect in that space or bend in that space. Now the high frequency ones of short wavelength, these ones they're going to be small, so they're going to be repeated like quickly, and they're going to be in relative to the space, they're going to be small. So they're going to travel in the space like rays. So they are easier to predict, as we can see in here. So a small wavelength, which is a high frequency wave sound, we can predict it more than a low frequency sound of that has a high wavelength size, a longer wavelength size. Now let's have a look at the types of interactions of sound within a space. We have reflection, as we can see in here. We have diffraction, refraction, and absorption and transmission. Now I'm going to talk about each one of them separately. Now reflection is easy, as I said earlier. But and first thing, we have to look at the wavelength of the sounds in a space. If the space is large, this is perfect. Even the like long wavelength we can predict it in that space if it's large. Now, if the space is small, you can't predict for the long wavelength. You can only predict for the high, for the small wavelength only for the high frequency sounds. So when we know we can predict the sound, the rule of reflection is this one. An angle of incidence equals angle of reflection, meaning, for example, we have this person, he is talking, so his sound will travel in all directions. This is one of the directions. So for example, we have this direction, we have this direction, this direction. Now we took one of the directions and we want to see how this direction will reflect off the surface. So first it hit this point. Now at this point, I'm going to draw a perpendicular line that meets the surface at this surface that meets this point here in intersection. So this line is perpendicular on this surface. Now around this line, I'm going to draw the same exact angle on the other side. So this is the incident angle, this is the reflection angle. They're exactly the same. And this is the reflected ray accordingly. So this is the rule being used for reflection in sound. And the same applies if you have, like, for the other rays, for example, the sound also traveling here. So it's going to hit here. We're going to draw a perpendicular here, so it's going to travel like that. Okay. Now let's have a look at the other interaction, which is called diffraction. Now diffraction is if you have an edge, the sound is going to bend at that edge. But that you have to take note that the bending is going to be toward the inside. For example, if you can see this edge, so this is the edge and this is the sound, original sound. This is a mixture of frequencies. So when it hit the edge, it bent inside toward the edge to the inside. And this one also bent inside. But as we can see, the high frequency sounds actually bend less than the low frequency sounds. Low frequencies, they bend more. This is an example in here. Low frequency bending more, high frequency bending, but at a little, very little bending. As we can see in here, this high frequency, this is the small diffraction, it's bending to the inside. This is a mid-range sound frequency, so it's bending also to the inside a little bit. This is a low frequency sound, it's bending a lot to the inside. So it's not the term actually is diffraction, but I'm saying bending just to understand what I mean by diffraction. Now, this is also another example of diffraction. So when you have a hole in the wall or in a door, maybe for the keyhole, so the sound will travel from one space to the other through that hole. How does it travel? So sound will travel, as we see, radially. So and then it hits this, like gets into this hole. It travels within this space. Then in here is going to diffract from the edges. So as we can see, diffraction going that way and going that way. This is how it's going to spread into the adjacent room. This is why if you have a small crack, a small hole, the sound will still travel to the adjacent space because it's going to diffract from the edges. Now this sound traveling to the other space is not going to be at the same intensity or loudness, but it's going to be like the same sound but of a lower intensity and loudness. Now refraction. Refraction is the least important interaction of sound in architecture. Refraction happens when sound travels from a cold area into a hot area. So usually this affects the sound from a sky to the earth. So if the sky is warm, as we can see in here, and the earth, like air near the earth is cooler, so the sound will bend more toward the earth. Now, if we have the opposite, the sound will bend outward. So whatever happening, so for example, if we live in an area of like an area where the air is cool near the earth, but it's warm up. So the sound of airplanes will going to be more, like a higher loudness. Now, if you have the opposite, the sound of planes will actually refract upward to the sky more, so we won't hear it. So, for example, we live in Riyadh, so the warm is actually the earth is warm. So what's gonna happen? We actually hear the noise of the planes less than a country that is cold. As I said earlier, this is not important for us as architects, especially for buildings. Now let's have a look at the other two very important interactions of sound within a space. We have absorption and we have transmission. Now we put them in one slide just to differentiate between them, because the thing is, as we can see in this example in here, we have these sounds coming in, then hitting the wall here. So the sounds are going to have three interactions simultaneously at once. The first thing, some of the sound will be reflected off. The more reflecting the surface, the more reflecting the sound will be. But we can never have a zero reflective, like 100% reflective material. Like, okay, a material might reflect off the sound, but still might absorb a little maybe or transmit a little. Okay, so you characterize each material by the percentage of each of these three interactions: transmission, absorption, and reflection. So, for example, if you have this incident sound hitting this wall, so if 70% is being reflected off, then this is a reflective material, even though like some of the sound is being absorbed or transferred to the other side, transmitted to the other side. Now, this is how you characterize the materials. Now, let's talk about absorption and transmission. So as we can see here, part of this sound is being reflected off. Now, the other part is going to keep going inside. So it kept moving inside and transmitted. What is being transmitted, not all the sound waves are being transmitted. Some of them are actually got trapped inside the wall. So this is what we call is absorption. So the ones being trapped inside or actually dissipated in energy, they are absorption. Now what happens is when the sound travels through a medium, through a wall or any material, now it causes the sound is made of energy, and this energy is going to travel through the material, and the material might have like gaps or some air sacs in between. The more air sacs you have, the more walls you have, the more friction you're going to have inside the material. So the more porous the material is, the more absorptive it is, because it's creating more friction. It's wasting the energy of sound into heat energy more by the friction. So you're going to have an absorption happening here. Now, whatever survives the absorption and survives the reflection is going to be transmitted to the other side in here. So as we can see here, they all occur simultaneously, and materials are being labeled according to the type of interaction that is strongest. Now let's have a look at the sound amplitude declination. Now, for example, I'm talking in a space. Now, people near me, like 1 meter away from me, will hear me more than people 10 meters away from me. This is because my sound actually, as you go further from the sound source, is going to decline, to have a lower volume. Now, this declination, we want to know how does it decline? In what ratio does it decline? Is it a linear equation, or is it square equation? We want to know. It actually depends on the source, whether the source is a point or a linear source. So we have to in these two types of sources. We have the linear, for example, we have the street. There's no point in the street that is creating the noise. We have a line creating the noise, and the noise is traveling parallel to that line, to that highway or street. So it's being transferred by parallel intervals. Now, if you have a sound source of a point source, it's going to travel in circles around the sound source, and the larger the radius, the less the sound will be. Now let's have a look in here. So in here, how it travels in the point source is different than the linear source. As you can see here, the equation is linear, and the equation in here is actually decreases with the square of the sound. For example, let's have this car, okay, this street, and let's say after 10 meters, the sound is decrease. After 10 meters, the sound is 100 decibels. Now, if you go further, like another 10 meters, the sound will be half, will be 50 decibels. Actually, not the sound itself, the declination. So, for example, after 10 meters, the sound was decreased by, let's say, 10 decibels. Now, after another 10 meters, the sound is going to decrease by another, like in addition to the 10 decibels in here, by an addition of 5 decibels. So it's going to decrease in here 15 decibels. Now in here, so we had already in here decrease in 15 decibels, and here going to decrease further, like 1/3 of the 10 in here, decibels decrease in here. So this is what we call a linear equation. Now if you have, we have a look in here at this one. So for example, the sound source is 100, and here it decreased by, let's say decreased by 40. Okay, after 10 meters. Now, if here the decrease by 40, now after another 10 meters, the decrease will be 10. So you see, there's no linear decrease. There's like a sharp decrease. And here it was first 10, then 5, then half of the 5, 2.5. You see, this is a linear declination. In here, no, it's a very sharp one. First was 40, then it's going to be first, yeah, it was 40 decibels decrease. It's going to be like a 10 decibels. So there's a difference in declination here. It's not linear. So you understand. I hope you understood this part, and you can always refer to these two diagrams to calculate. Now let's have a look about reverberation time. Reverberation field reverberation time. I mentioned earlier in this lecture the term reverberation. So I said there is something called echo and we have something called reverberation. Now, echo is the sound traveling, then hitting the wall, then like reflecting back to the people sitting here. So they will hear first the words from this person coming directly, then they will hear the reflected sound again. So they will hear the same word at two different times, maybe 1 second or more difference between them. Now, reverberation, what happens is this person is talking, so the people in here will hear it, and the people in here will hear it. What happens, people at the back, they will receive the words from here, and they will receive like the reflections coming off these words. But these reflections are not as strong to like hear it as an echo or a word. So they are like overlapping. So this is what we call is the reverberant field, where the like sounds are overlapping and like somehow they're not like the speech is not too clear. Okay, because of the reflections happening in that area. Now, reverberation time. Reverberation time is a term we use in design. This is very important for us as architects and interior designers as well. It's important. Reverberation time is you measure how fast does a sound die. For example, this like will determine for you if you have an echo or not. So for example, an echo you need not echo. For example, this person is speaking. This reverberation time will tell you how long will it take this sound coming from this source to die 60 decibels. For example, his loudness is 100 decibels, and I want to know in what time will it reach his sound in this area reach 40 decibels, will die, decrease by 60 decibels. So, for example, let's say it took him 1 second. So if it took him 1 second, it's fair enough. This is good for speech. But for example, if it took him to die, like the sound to decrease 60 decibels, maybe 5 seconds, this means that his sound was being reflected back and forth for a very long period, because 5 seconds is a long period of reverberation. So this is actually a noisy in reverberation time. So the shorter the reverberation time, the quicker the sound dies, the better for speech. The more it takes the sound to die, this means there's more reflection. This means the long reverberation time, more like it's being used for music uses, not for speech. But you need to actually learn the definition in here. The reverberation time is the time it takes a particular sound to drop by 60 decibels in loudness. You can have a look at this one. This is like explaining to you how this person is speaking. See his sound. First, his speech is reaching directly to the people. Then his sound is still like lingering in the space. It didn't die quickly by people like hearing his first words. His words will keep on reflecting in the space. So the longer it takes to keep on reflecting, the more the reverberation time. The least the reflections, definitely it will cause the least reverberation times, the better for speech. So usually if I want to decrease the reverberation time to make it absorbed quickly and decrease quickly, I need to, for example, avoid these reflections. Maybe I'll put absorbing materials on these walls and surfaces. So this is the reverberation time. So before we look in here, I want to actually try to hide these in a way. Don't look at these ones. So we have two things that affect the reverberation time. Now, I first mentioned in here, if I add absorbing materials, I will make the reverberation time shorter. So this means the higher the absorption in a space, the smaller the reverberation time. So the relationship between reverberation time and absorption is inversely proportional. Now let's have a look at the other function, which is the volume of a space. So the larger the space, for example, let's have a look at this classroom. So let's see in here, we have many reflections. If I had like a wall in here and we don't have this area, this space is this small. As you can see, the sun will like reflect back quickly and die quickly because it took like a shorter period to reflect back to the people in here. So this means the larger the space, the more it takes the sound to reflect back to you. It takes maybe 5 seconds, 10 seconds for the sound to come back to you. If you had a smaller space, the sound will come back quicker, so you won't hear it as echo or any type of noise. You will have then less noisy space. So as we can see in here, the larger the volume, the more reverberation time, the more reflections happening, the more time it takes for the reflections to travel in the space. So it's directly proportional. The reverberation time is directly proportional to the volume of the space. Now the absorption, how do they actually calculate this S value? We're not going to use this equation, but this is for your information. So for example, we have this space. Is it enough to put, for example, carpet, or does it matter if I added the curtains as well? Definitely. Every material you add to a surface, the more absorption you will have. For example, I have 5 surfaces in here. I have the walls, I have the floor, I have the ceiling. If I cover the floor only, okay, I decrease the reverberation time, but not too much, only maybe 1/6 of the possibility I could do. If I covered also the walls with absorbing material, then I'm increasing the absorption even more. So the more you cover the surfaces, the better. And now the other thing that affects the absorption is actually the type of material you are using for absorbing. As we mentioned earlier, like each material reflects some of the sound and absorbs some of the sound. So the higher the absorption of the material, if the material is absorbing more than it reflects, the better. It's absorbing more. So what they do is in calculation, they, for example, take the area of this curtain and multiply it by the coefficient of absorption. Then they do the same for this carpet. They take the area and multiply it by the coefficient. They do this for all the surfaces in the space, then they sum them up. As we can see in here, this is the absorption of surfaces given in sabbaths. This is actually the summation of all the absorption in the space. Like I said earlier, we are not going to do any calculations for that, but we just need to understand it. And the most important thing is you just need to know the volume. The larger the space, the more reverberation time, the more it takes for a sound to die. Now, the more absorption, the less it takes for a sound to die, meaning the shorter the reverberation time. So we have two types of spaces. We have spaces where I want to encourage speech, and I have spaces where I want to encourage I want the reverberation to be there. I want it to be a longer vibration. For example, music. I want to keep like overlapping sounds. This makes the music more appealing to my ear. So, and there is not no certain information I want to hear from the music. So, if I want to have a speech, I need to make the space as absorbing as possible. If I have like I use a function of a music, so I need to make the space as reflective as possible. Of course, definitely according to my uh, needs in that space. Now let's have a look at the biology of sound. Now, biology of sound is how actually our ears will hear the sound, how actually the sound will enter our ear. So it's not about the perception. Perception is how the brain will decipher whatever the ear got into our system. So biology is talking about the ear and the signals being transferred. Afterwards, whatever we perceive is being done by the brain. We don't need to know all these. We don't need to know them in details. You just need to know in general we have an eardrum. This eardrum is being sensitive to the pressure of air. Now, as we said earlier, sound waves, they are made of pressures, like high pressure, low pressure. This is creating the sounds. So this is why we have eardrums. They vibrate with the sounds, and this is how we take in the information of sound. So these vibrations are being transferred into these nerves through some liquid in here and being deciphered and interpreted later on by the brain. Now there is something that you need to know. Now as we said earlier, the sound is pressure. But the thing is, our sensitivity to that pressure is not linear. Meaning, if I heard a pressure, okay, a certain pressure, I will hear it at a certain loudness, let's say. Now, if that pressure multiplied by 10, my hearing won't hear that sound multiplied by 10. We'll hear it at a different case. I'll give you a better case. For example, I have the first pressure, I heard the first pressure at a certain level. Then this pressure doubled, not doubled, multiplied by, let's say, 100. Now the pressure multiplied by 100. Okay, but I'm not going to hear that sound multiplied by 100. I actually am going to hear it as 4 times louder. Why is it 4 times louder? Because our ears actually interpret the intensity, are sensitive to, it's not linear fashion, it's non-linear fashion, it's actually a logarithmic fashion. Okay, so actually our ears use this scale, the logarithm of the intensity. Meaning, if it's multiplied by 100, then I'm going to hear it as double. If it's multiplied by if it's going to hear it by multiplied by 4. If it's multiplied by 100, I'm going to hear it multiplied by 4. If it's multiplied by, for example, by 1000, I'm going to hear it multiplied by 8. See, it's not a linear, it's a logarithmic. Now, I will tell you later on why is it 4 for the 100, why is it 8 for the 1000. First of all, let's have a look at this equation. As we said, our ears are sensitive to sound using this equation. This is how we convert the pressure into decibels that we can relate to. So this is the equations. As we can see, we multiply 10 times log of the difference between the lowest pressure a human can hear and the pressure of sound you want to actually measure its loudness. Now the thing is, before I go into this one, what does P1 mean? Now, as we can see, sound is pressure. And pressure can go very low and very high. The thing is, our ears can't hear all levels of pressure. It can hear a lowest limit of pressure and a highest limit of pressure. So for us as a humans to create this scale that would start from 0, we said, okay, we will make the lowest pressure we would hear as a humans is considered a 0. It's not actually a 0 pressure. It doesn't mean there's no sound in here. There is sound, but this is the lowest sound a person can hear or can be sensitive to. So P1 is actually the lowest pressure I'm sensitive to, and P2 is actually the sound you are want to measure in decibels, its loudness. So usually we don't want to know. Usually we don't give you like what is P1, and we don't give you what is P2. We just give you P2 is a multiple of P1 by how much? For example, in here, if sound is increased by in intensity by a factor of 10,000, see, I told you already. P2 is P1 times 10,000. So P2 over P1 is actually 10,000. So this makes easier for us now to understand. So the factor between P2 and P1, replace these two with this number. Now to calculate this 10,000 of increase in intensity, what does it mean in decibels? Okay, I have a sound, I increase it by 10,000 factor, okay? This means the sound is increased in decibels. How much? 10 decibels, 20 decibels, how much? This is how we calculate it in here. We put the 10,000 in here. So 10,000 is actually 10 to the power of 4. So log of 10 to the power of 4, you remove the 10 and you keep the 4. So in here, it's going to be a 4. Then you multiply the 4 by 10, you get the 40. See how we got the 40 decibels? So 10,000 a multiplication of sound or pressure means increase in decibels by 40 decibels. So this is the equation we usually use. You need to learn this example. You're going to get something similar to it. You need to understand it. Okay, you're going to learn. You have to also memorize this equation and how we are going to use it. Now, why do we have a 10 in here? You might ask this question, which is actually explained in here. We don't need to know this for this course, but if you are that curious, you can have a look at it in here. So actually, the measurement is bell. See, then the increase in here is 4 bell, but because we are 4 bell means that the sound will multiply by 16 times. So it's a major. So if I'm like measuring, for example, 1 bell, I'm going to have a multiplication by 2 of the sound loudness. I'm going to perceive it as twice. So that's why I need to have like an integer that I can say, for example, instead of saying 1 bell, maybe I can say 0.3 bell, 0.4 bell. So to make it easier for me, I said, okay, I'll multiply it by 10, but instead of having a bell, I'll put the DC. So the DC is actually divide by 10. So we put the DC to add the 10 in here and make it easy to measure. Okay, you don't need to know this one. If you found this one confusing, you can just skip that part. So this is the scale we got in here. So we got the decibel scale. So as I said earlier, 0 decibels doesn't mean 0 pressure. It means this is the threshold of hearing. We start to hear at this level. This is the pressure that I can start hearing. So it's 0, I consider it 0 decibel. We made the scale accordingly, and we can see intervals of 10 decibels each. Now, later on, I will show you that every increase in 10 decibels means that you are going to hear the previous sound as double, meaning a noise of 40 decibels loudness and a noise of 50 decibels loudness. The 50 decibels, if you're going to hear it, you will find that it appears to you as double the 40 decibels, while actually the difference is only 10. Okay? Certain noises in here are like we are giving you examples to imagine. What do I mean by 10 decibels? What do I mean by 50 decibels? So for example in here, and is it noisy? Is it quiet? So as we can see in here, they are divided in here. So we have the quiet between quiet and noisy. So this is the normal in here. Average residence is almost at 40 decibels. Now, office activities, usually offices are not that quiet. They're not a quiet environment. They are somehow noisy, but at a lower level noisy. So usually they should be at 50 decibels. Now, if they are increasing these numbers, then there is actually a problem in these spaces. They are creating too much noise, which you have to actually address in your design or in your maybe HVAC system or any other implementation you will use. So this is not what we are talking about now. We are talking about the scale and understanding the scale. Now, I mentioned earlier for you that our ears, they are not sensitive to all frequencies the same. Meaning, like I said to you earlier, we have the vowels, we have the consonants, we have different sounds. So I'm saying vowels and consonants because these ones you can actually relate to, or you can like quickly pick up when I talk about them. So consonants, let's say it's the letter T and S, okay? It's not S, let's say T, B, P, these letters, okay, consonants. And we have the vowels like O, we have A. So we don't like the vowels are actually the transition. So when I say A and when I say P, you will hear the P like louder than the A. But the thing is, the P, they are both actually having the same volume. I'm saying volume, not loudness, volume. But because my ear is more sensitive to the P, to the high frequency, I will hear the P as louder. So see how I'm using the words volume and louder. So louder is actually the volume that my ear hears. The loudness is actually what I perceive. The number, like the loudness, the volume I perceive. It's not the actual, it's my perception. Because it's affected by the frequency of the sound. It's affected by the frequency of the sound, what type of sound I'm listening to. Okay? So our ears are more sensitive to a certain frequency, as we can see in here. It's this one, 4,000 hertz. So you need to actually memorize this number, and we are least sensitive to lower frequencies, as we can see in here. As we go from 20 hertz to 500 hertz, we are least sensitive. Okay. As I said earlier, the threshold of hearing is not a zero sound pressure. I told you that earlier. And why is that? If you don't remember, go back to the recording and listen to it again. As we can see, we have the scale, but as we can see, these ones, they are like labeled extremely loud, painful. These ones, they are not like usual loudness. They might happen, and when they happen, they can cause some serious issues for our ears as humans, and they might cause some deafness too. Now, as I said earlier, the ear responds to, so the ear will you will hear a sound based on two factors. First thing, it's amplitude, it's volume. So if you have a sound of a low volume, you won't hear it because it's a low volume. Maybe other sounds will mask it and cover it up. And the other thing that our ears will respond to is the frequency, the information, the type of sound you are listening. So as I said to you, we can't hear all frequencies. The same thing as we can't hear all pressures. So we have a limit for the pressure of sound. Very low pressure, we can't hear it. Very high pressure will cause us damage. Now the frequency, very low frequency, we can't hear it. Animals would hear it, but our ears can't detect it. And very high frequency, we can't detect it either. We only have this range from 20 hertz into 20,000 hertz. Now, as we can see, in here, so we have put the human speech where like all the letters, any type of sound that can come out of my mouth, we put its range in here. As we can see, the lower frequency are the vowels and the higher frequencies are the consonants. And this dashed line is the B. This is the 4,000 hertz that our ears are actually most sensitive to. We hear the loudest. Okay. And as we can see, the range of music actually spreads even more. They have more of the range of the low frequency sounds and a little bit of the high frequency. Now, most of the information in sound is actually changes in frequency. So how do I differentiate a word? A word is made of letters, different letters, of a transition of vowels. So I detect a word by detecting these difference in frequencies. So I detect like I have more than one letter. Now, as I mentioned earlier, we are different. We are sensitive to different frequencies more than the other. And we have very low frequencies, we have very high frequencies, we have mid frequencies. So they actually divided the frequency range into 10 intervals, which they call them octave bands. And to make it even easier, as we can see here, octave bands, to make it even easier, they divided them into a more general octave bands, which are low, mid, and high. So us as designers, we just know them as architects. We just need to know them as low frequencies, mid frequencies, and high frequencies. And usually the decibel scale actually differs from one frequency to the other. That's why you find dBA, dBc. So it's actually based on which frequency you are measuring. But for us as designers and architects, we're not going to go through that. We are going to use the general one because usually we have more than one frequency overlapping each other. So we're not going to go into that dilemma. We're not going to go into more detail about this one. You just need to know we actually divided them into three bands. So now let's have a look at the perception of sound. Perception of sound. Now we learned the physics of sound. We learned the biology of sound. Physics is the actual how the sound travels in the space, how the particles of sound vibrate in the space. Now the biology, we learned how these particles, when they vibrate and hit our ear, how they go inside our body. Now, the perception is actually how the brain deciphers these sounds. And when we have certain conditions regarding the sounds, how does the brain detect them or ignore them or for example, combine them? So we have these phenomena in here. So they are not like 1 plus 1 equals 2. You have to understand them so you can do like analysis for a situation and know how sound is going to actually act in that situation. So we have something called phenomenon of loudness, and we have phenomenon of apparent source. We have phenomenon of echo. We have phenomenon of noise, dead and live spaces, and gender recognition. Now let's have a look first thing at the phenomenon of loudness. Now loudness, for example, I'm a person, you are a person, we have different ears. So let's give you another example. You are a person, you have your grandmother. Her ear is a bit old, okay? So she can hear you differently than you. So as we can see, loudness is actually affected by certain factors. First thing is the age, okay? Which is mentioned in here, age and health of the hearer. Maybe two people of the same age, but one of them has problems with his ears, so they will hear differently the loudness. Okay. Another thing is the sound pressure. This is how you hear the loudness in the first place. So the higher the amplitude, the higher the loudness, definitely, and the lower the amplitude, the lower the loudness. Okay, and the frequency of the sound, like I told you earlier, like we mentioned earlier, the higher frequency, we have a frequency of 4,000 hertz. So this is, I'm going to hear it as more loud if it actually had the same volume as another frequency of, let's say, 100 hertz. Yeah, this is because our ear are more sensitive to that frequency. So it depends on the frequency, and also it depends on the presence of a masking sound. What do I mean by a masking sound? If I have more than one sound happening all together, if, for example, you are talking and you have loud music in the room, actually that loud music, no one will actually hear what you are saying, probably hear what you're saying. So this is the phenomenon and the presence of masking. There is something that actually covered your sound. Now let's see when actually a sound would mask your a certain sound and how to calculate it and how to find the resultant loudness at the end. Now before we go into that calculation, first of thing in here, let's have a look at how we actually perceive the difference in loudness. I mentioned to you earlier, like if every time you increase or decrease 10 decibels, you will hear the sound as either doubled or half. So 10 decibels difference means double, okay, or half. Now 20 decibels, what you're going to have every 10 decibels you are adding, you're going to double the sound before it. So for example, when I added the first time 10 decibels, I actually doubled my loudness. Then I added another 10 decibels, so I doubled the double. So first time I multiplied by 2, then I'm going to multiply another 2 to the number. I'm going to have a 4 times loudness. Imagine a change in decibels is 30 decibels. What's going to be the resultant perception? So you're going to multiply actually the first time you added 10, so it's 30. The first 10 is multiplied by 2. The second 10 is multiplied by another 2, so 2 times 2, another time 4. So the third 10, you're going to multiply again your resultant by 2. So the 4, you're going to multiply by 2 again, you're going to get 8. So if you actually add 30 decibels, you're going to get 8 times perception of loudness. Okay. And let's have a look at the, okay, if 10 decibel is actually doubling, this is too much. What are the sounds that I will notice and barely notice or notice majorly? If you add 30 decibels only, it will be barely noticeable, meaning if you have an addition of 1 decibel or 2 decibel, you won't notice it. You will only start noticing if you there's a difference of 3 decibels. Now the 6 decibels, you will notice it. You will find the difference. Yeah, this sound is louder than the other sound, or there's a 6 decibels difference. But it's not going to be the same as 10, which is like double that loudness. So you need to memorize this one, okay, and understand how here each time I add a 10, I'm going to multiply by 2. Okay. So these are the rules of thumb for calculating your resulting loudness. Now, before I go into that one here, let's go in here. Now, if I have 2 sounds, the actually resultant sound is going to be affected by their difference, meaning I'm talking and there's a person talking next to me. If I am louder than him, let's say by 1 decibel, this is my graph. So the difference in, I'm louder in only 1 decibel. So I will look, as we know, 1 decibel is not noticeable. Now this graph, if we have a look at it, what it means is, first thing, if you have 2 sounds, if one of them is higher than the other, you will take the highest loudness. Then you're going to add a number you get it from this graph to that highest to get your resultant loudness. Meaning, my speech is at let's say 30 decibels, and the person next to me is 29. So the difference is 1 decibel between me and him. So at first, I'm going to take my 30 decibel and add whatever I get from this graph. So our difference is 1 decibel in here. So if I have 1 decibel difference, I'm going to add, as we can see in here, 2.5. Okay. If we are identical, I'm going to add 3. If I have a difference of 10 decibels, I'm going to add 0.5. Now what we get from this graph, the more difference it is, if you have, for example, 10 decibels difference, you don't have to bother to go through that graph. Just take the highest and that's it. Adding 0.5, adding 2, adding 1 is not actually important. You just just take the highest. Now, if they were very close to each other, actually they would affect each other. They would increase the loudness. For example, if I have 2 identical sounds, so the difference between them is 0, 0. So I'm going to add to their loudness 3 decibels. If like a difference of 1, I'm going to add 2.5. If I have, for example, a 5, then I'm going to add a 1. 1 is not something like you would notice. Actually, anything below 3 is not something you would notice. That's why the whole graph thing, you just don't have to use it. We will use these rules of thumb. Now, these rules of thumb, as we said, notice in here, 2 identical sounds, you add 3 decibels. So as we can see in here in this one, we have number of identical sources. So if you have 2 identical sources, you need just to add 3 to one source, 3 decibels to one source. And the increase in loudness of 2 people talking, singing, or talking at the same time at the same loudness will be just barely noticeable. If 4 people will be 6 decibels addition, will be noticeable. It will be that much, but it'll be fine. You'll notice it. If you have 10 people, it'll be like doubling the sound. Now, if you have 100 people, you will have like 20 decibels addition. 20 decibels means 4 times louder. See, these are like, actually memorize these ones, okay? How many, the number of identical sources, what's the addition in decibels? Now let's have a look at the rules of thumb in here. So the first one, to combine 2 sounds of almost equal loudness, like we mentioned in here. what you have to do is just add 3 decibels to the louder sound. Okay? Now, if you have 4, if you have 10, then you're going to refer to this table. Now, the second rule of thumb, if you have 2 people of not equal loudness, there's a noticeable difference, you just take the highest one. See, use the decibel of the louder source only. You don't bother calculating the difference in all this. Just, for example, 40 and 42, take the 42. This is the resultant. Now, if you have like 4 people talking and each one of them has a different loudness, then what you are going to do is combine any 2 of them using any of these rules, then combine the resultant with a third one, then combine the resultant with the fourth one. Just like keep combining the resultants. For example, I have 2 people have a loudness of 20 decibels and a third person of 30 decibels. So what you are going to do is you're not going to say from the start, oh yeah, 20, 20, and 30, I'm going to take the 30. The 20 is very low. No, these 2 people actually might do an increase, so you need to find their resultant. So 20 and 20, you'll have to add a 3 decibels. This is a resultant of 23 for these 2. Now the third person is a 30. Now 23 and 30, definitely there's a big difference. You'll just take the 30. Now let's make it a more logical comparison. For example, you won't have that like 10 decibels difference. 10 decibels means like twice the loudness. For example, people almost at the same loudness. Let's say, for example, 40, 41, and then 42, and then another 42. What you're going to do is take the identicals first, 42 and 42. This is a resultant of 45. Now, 45 and 41 and 43, let's say, 45 is actually larger than them, so I'll just take 45 from the start. The first thing is just take the identicals, calculate the resultants, then do comparison to the other sounds in the space. Okay, now the second phenomenon of apparent source. This one, if you were in class, you could have experienced it more. The thing is, for example, try closing your eyes and ask someone in the room that you don't know where he is standing just to speak. You will actually determine his location by just hearing his voice without seeing where he stands. This is because we have 2 ears and our ears actually calculate see in here, this is the source, and I have this ear and I have this ear. See this small difference in here? Actually, our ears will actually calculate this small delay, and actually by calculating this small delay will tell you, okay, I heard the sound first on the right ear. This means the sound source is actually closer to the right ear from the left ear. So the sound source is on the right. So this is the phenomenon of apparent sound, apparent source. Our ears will actually find the difference in times where the sound will reach our ears and find if they are identical or there's a difference. If they are identical, meaning the sound is either in the center, in the front, or in the back. Okay. Now we have these examples. Like these are different scenarios. As I said earlier, like these perception phenomena, we need to understand them so we can like analyze them or apply them to different scenarios or cases. Let's have a look first at this case. As I can see, I have 2 speakers, A and B. Now, what do you think is going to happen in here? Now, if I have 2 speakers like symmetrically located, the distance from B to here and A to here is the same. So our ears, when this happens, what's going to happen is our ears are not going to say, I have 2 different sounds coming from the sides. Our ears were going to detect that the sounds are coming from are coming at the same time with no delay from either. So our brain will think that the sound is coming actually from the center, from the front of us. Okay, so it's going to be from here. Now let's have a look at the second example. 2 identical sources vertically separated. As I can see in here, this person is sitting, and I have a person talking here, and I have speakers of his sound, but at a louder volume here. Now the thing is, when I look at the sound coming from this person and right above him, so I want my ears also, again, won't detect any difference. It's going to detect only the right and left. So if the right and left are at exact distances, it's going to see it from the front. Now when I look in the front and I see a talking person and I see a speaker, which one of them will my brain think is talking, doing the talking or the loudness? Definitely the person moving his mouth. So this is the phenomenon of a loudspeaker and a speaking person, where they are separated by a vertical distance. So I'm going to hear the sound in here, think the sound is coming from A. Now, sound reflected and the sound is blocked. Now, as I can see in here, I have a partition between me and the speakers. So the sound is not going to reach my ear directly here. I have this partition. So what's going to happen, the sound is going to travel, reflect off this wall, and come back to me. Now, when I hear this sound, I won't think that the sound is coming actually directly from the left or from the back. I will think that the sound is actually coming from the front left maybe. So as we can see in here, it will think that the sound is coming from point B, behind the surface, behind the wall. This is exactly the same as the concept of the mirror. So the mirror is actually a reflection of the image of the surface. So you will think that the image is somewhere inside in here, where it's actually coming from here. Same concept. Now let's have a look at the phenomenon of echo. As I mentioned earlier for you, echo is delayed sound that is perceived as a distinct and clear second sound. So you will hear the same sound again distinctively. So this means that the sound actually have a travel a certain time period, so you can hear two separate words. Meaning, if I heard the word directly, like within a short period, I will hear it as overlapping, or I won't actually hear it as a second word. I will just hear that there is augmentation or like increase in loudness of the word, maybe with some like reverberation. So echo is actually hearing the word again. So for echo to happen, or for you to actually hear distinctively another word again, there's a certain time interval that should pass. This limit should be a minimum of 60 milliseconds. So for us to be able to actually calculate it through diagrams, so they said, okay, that the speed of sound is constant. So 60 milliseconds is how many meters of travel of sound. So they calculated and they found out it means 21 meters. So actually, echo, to hear echoes, the sound should like take a period of reflection of 21 meters more than the direct sound. Now be careful when I say more, meaning, or as we can see, longer. For example, in this example here, we have direct sound and we have this sound, the echo is being reflected back to us. Now, when this person speaks, I'm not going to hear him instantly when he speaks. The sound will travel, then reach my ear. While the sound in here, direct sound, is traveling, this reflected sound has reached somewhere here. So I'm going to actually measure the 21, see if it's 21 or not, from this point. So it's easier for me to just like measure the summation of this line and this line and this line, then actually subtract the direct sound to see what is the difference in time interval. For example, direct sound reached me within 2 meters. Now the reflected sound reached me within 24 meters. Okay, let's be more let's have it more tricky. So let's say, for example, if the distance in here is 2 meters, and distance in here is 2 meters, and this one is 10, and this one is 10. So what we are going to do is, the distance of direct sound is 2 meters, and the distance of the echo is 10, and 2 and 10 is 22. Will I have an echo or not? I want you first, before I tell you the answer, to actually think. Will you have an echo or not? If this one is 2 and this one is 10 plus 2 plus 10 is 22. Will I have an echo given that it has to be a minimum of 21 meters longer? Now the answer for this question is no, you won't have an echo. And why is that? Because this one took me 22 meters to travel to me. But I have to subtract the time it took the direct sound to actually reach me to me in the first place. So I'm not going to measure this one on, I'm going to measure the difference. So the difference is going to be this one minus this one. So it's going to be 22 minus 2 is going to be 20. So 20 meters is this one, this time 21 meters. So there is no echo. If the value, the difference was at 21, then definitely, yeah, you will have an echo. If it was a 22 or even more, yeah, I will have an echo if you had it 21 and or more. Okay, now this is echo. There's another thing, another term that we call overlap. Also, overlap has even a shorter period of time to hear that your sound is being like overlapped in a way. Now, this period, now as for echo is 21, the period for overlap has to be even shorter. The period for overlap is going to be 15 meters. So if you had a 15 meters, between 15 meters to 21, okay, you won't have an echo, but you're going to have an overlap of sound. If you had less than 15 meters, then you won't have any echo, nor any reverberation, nor any overlap. Now, this 15 meter is not mentioned in this slide, will be mentioned later on in another slide, in another lecture, but this is just to inform you from now, so that later on you won't be confused by the two numbers. So 21 is the minimum for the echo to happen. Now, let's have a look at the other perception of sounds, the phenomenon of noise. Now, what is noise? How can you tell a sound is noise and a sound is not noise? Actually, it's actually depending on whether you want to hear that sound or not. You can't always call a sound a noise. It can be noise for you, but it can be maybe music to someone else, or needed information, or like important sound to someone else. For example, as we can see in here, now this person is working here, and this person is talking here. Now this person is talking, okay, and the person on the phone with him is actually wants to hear him talking. He wants him to be loud enough to get his speech across through the phone. Now this person doesn't want to hear whatever this person is talking about. So the sound for this one, the important speech or sound for the person on the phone, is actually noise for this person. So it's actually noise is actually a sound that you don't want. You have no needed information inside it. So as we can see here, we have a definition for noise: sound that carries no information for the receiver. You don't want to hear that sound, then you are considering it as noise. For example, if you are listening to for example, the person was using this hammer light instrument. Okay, it's going to be noisy for him. It's not going to be as noisy for him as a person crossing the street, because he knows he is digging. He knows he is expecting that noise to happen. For him, it's his job. He's doing his job. The other person will be like he's thinking about something else. This is like a distraction, like sound that he doesn't want to hear. Okay, now let's have a look at other characteristics or other things that would make a sound noise. Now, if a sound is very loud, this will be definitely noise. Okay, will be more annoying. The louder, the more annoying. High frequency, because there's a threshold, sometimes you might, okay, here's an information that you don't need, but if it's somewhere in the background, you won't consider it noise. It is just there. You won't listen to it. So if it was too loud, you will definitely consider it a noise. If it was too low, you won't hear it in the first place, or you won't recognize it. Now there is also the high frequency sounds and low frequency sounds. High frequency sounds are usually more noisy than the low frequency sounds. For example, as we can see in here, this is the wheels squeaking. Or for example, the doors when they squeak, this is a high frequency sound. So high frequency sound is usually noisy. An intermittent sound, we have something called intermittent, and we have something called continuous. For example, intermittent, if you are digging, for example, this person digging his instrument into the floor, so the sound is going to be like jush, 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 jush. So it's not going to be jush, no, it's going to be a lapse of between silence and noise. So this actually creates noise. We call it intermittent sound. Now, for example, if you had an example of the AC, the air conditioner is actually creating noise. But the thing is, creating as unwanted sound. But the thing is, that sound is being continuous. That's why you are able to keep it in the background, because there is no intervals of silences. So uh, you won't notice it. Now, okay, sound with information content not relevant to the receiver. This is actually the first thing I mentioned in this slide. Now, I think this is the last one of the phenomenons. Oh, yeah, before the last one. So now let's have a look at the phenomenon of dead and live spaces. This is actually directly related to the reverberation time. As I mentioned earlier, that it depends on the function of the space. If you want to make it a long reverberation time or a short reverberation time. So if you are using a space for a speech, you need to make it short reverberation time. You need the sound to die quickly so it doesn't have any overlap or echoes. So we call these spaces dead spaces. Dead spaces have short reverberation time. They are usually absorptive, they are usually small and cozy. Now, live spaces, they are usually used for musical instruments or musics. Okay, so you want to, the more reflection, the better. Okay, we call these spaces live spaces. So they need to have more reflections, more reverberations. So it has to be long reverberation time, as we can see in here. And the larger the space, the better, the more reflective the surfaces, the better. Now, these reverberation times are actually, they like, according to the space used, they actually determine what is the suitable reverberation time according to the space. Now, the reverberation time is never zero. So if I want to have a dead space, I can't say, okay, reverberation time must be zero. No, as I mentioned earlier, reverberation time is actually the time it takes the sound to decrease by 60 decibels. So if I want a space that is suitable for speech, okay, my sound should decrease within 1 second, 60 decibels at least. Okay, now if I go into the other spaces, these are the recommended reverberation times for them. The more light music is less reverberation time than the high orchestral music. Now let's have a look at the phenomenon. Now, as it goes for this slide, if you want to memorize them, you need to know the speech needs to be 1 second, and the musical festival they need to be about around 2 or 3, but not actually memorized. Like you just need to know it can reach up to 3 reverberation time, and for speech you need a minimum of 1, actually a maximum of 1. Okay, now let's talk about the phenomenon of gender recognition. Now you can tell by actually listening to someone's voice by not looking at them if they are a female or male. Why is that? It's because actually the sound coming out of a female is different than the sound coming out of a male. In what way it's different? Now they graphed both sounds coming from the male and female at different frequencies. So these are the frequencies and their sound intensity, which is related to loudness. And they found out that when I, for example, say when I when I speak, the sounds of high frequency are at a higher loudness, are at higher intensity. And the sounds at a lower frequency are actually of a lower loudness. That's why my voice as a female is being characterized as high pitch or a high frequency. Now, when we go to the male sound, actually male have higher intensity at the low frequency sounds, and lower intensity and lower loudness at the high frequency. That's why they're characterized by these frequencies more, the low frequencies. Now, as it goes to sound and health, so as we mentioned earlier on the decibel scale in here, there's a limit to what we can endure in loudness. We can this is the threshold of hearing 0. Then we can go up. The up we go, the further we go, the more noisy it can be. Now there's a noise level that you should not actually trespass, which is the 75. 75 is actually considered loud, but if you actually trespass that sound level, if you go above 75, you will start getting health issues such as sleeping problems, headaches, and other anxiety issues. So you need to decrease your level to keep the sound level in a space as much as possible, like 70 or below. Above 75 or 75 is not good for the health. Now, there's another thing you need to take into consideration also. For example, I can endure the 75 decibels, but can I endure it for a long period of time or a short period of time? Or it doesn't matter the period of time. Actually, it makes a difference. Imagine yourself entering, for example, when you go shopping, you enter a store, okay, you start shopping, there's loud music. In the beginning, you're fine with it. Then at the end, you find that the music is actually too noisy for you. This is because you could endure that loud music for a certain period. After that certain period, it started to be causing health issues for your body. So any recommendation of sound needs to be like connected to the duration of the sound. So in the US, the work has prohibited exposing workers to noise levels above 85. So for them, 85 was the limit. But they also limited that 85 to a duration of 8 hours. Any duration of more than 8 hours, more than 8 hours has to be even less. Now, if, for example, if I'm exposed to 100 decibels, for how long I can endure it? For example, they are in this example they are saying you can't exceed actually 1 hour. So see, the higher the level, the higher the loudness, the less you can endure that loudness in order to avoid health issues. Now let's have, like I mentioned for you, how they use the psychology, or they use this phenomenon of perception and noise and loudness in the stores. This is actually used, for example, when you go shopping, that you can endure it for a couple of minutes, where you actually maybe collect a couple of items in the store. Then when you start feeling that it's getting noisy, instead of staying in the store and trying them out, or thinking about getting them or not, just go to the cashier and buy them right away to just get rid of the store. So this is a psychology they use, like they make use of this phenomenon for their own benefit. Another thing they can use, now this is when you want to just stay in the shop for a couple of minutes and leave it quickly. Now sometimes this is not the goal of the shops. For example, if you want to be in a grocery store like this one, Target, it's a very large supermarket. You want to stay, they actually want people to stay in it as much as possible, to take their time to think, to keep grabbing things, to keep seeing things, and keep collecting things and buy them at the end. So what they want to do is actually create a very comfortable environment for them and a very quiet environment for them. So in order for that to happen, they're going to have no music at all. They're not going to put any type of music. Actually, they're going to probably put something called white sound. White sound may be the sound of HVAC system, which makes which would mask the noise in the area, which would make the space more comfortable sound-wise. Now, at the end, let's have a look how uh, the sound is being seen in the design. So we have the source of sound. So this is the noise system. You have the source, you have the path where the sound travels or noise travels from the source to the receiver, and you have the receiver. Now, for me as a designer, sometimes the source is a noise. So I want to control that noise. Now, I want to see where my job as an architect, where is my role as an architect in this noise system. The first thing, the source, sometimes I can like affect the source by specifying, for example, less noisy mechanical systems, try to enclose them separate from the other spaces, for example. But then sometimes I can't control this one much. I have it and then I have to design according to it. Then the second part that I can like actually alter with my design is the path. I can just change the zoning of the areas. I can change the partitions. I can change the openings. For example, you have a highway street and you have your villa, for example. So you want as much as possible, try not to put any windows facing the high street, because definitely you are facing the noise. So in this way, if you make the windows away from the high street, you are not controlling the source, definitely. The source is there. You are controlling only the path. So this is our role as architects in this noise system. Now the receiver also, I can't say for the receiver, please block your ears. I have no control over the receiver. The receiver is there and will hear whatever reaches to his ear. This is it for this lecture. I hope you go through it. I hope you understand everything in it. If you have any questions, please email me or please come to my office during my office hours.